All right, this is 2019, number 3. It's a 10-point problem originally. The back half, the last 5 points are all buffer stuff, so we're only looking at the first 5 points of this thing today. The national average on this thing was 3 points out of 10, and so pretty much everybody got the buffer part wrong, and then missed some of this too, and so you may be able to beat that just in the first half of this problem. So here we go. It's supposed to take you 20 minutes, but we're eliminated half of it, so if it takes you 10 minutes, you're in pretty good shape. So here we go. This is 3A. This is the free point on here. Students given 50 mils of a solution of sodium carbonate. Don't know the concentration. To determine the concentration, the student's going to mix it with excess calcium nitrate. This is important. Excess calcium nitrate causes a precipitate to form. We should recognize sodium's always a spectator, nitrate's always a spectator, so it's carbonate and calcium that are going to form the precipitate. They give us that formula, which is really sweet of them, and then they ask for a net ionic equation. I talked about they don't ask for, there's no net ionic equation question. Now they work them into other questions. So here it comes. The sodium's a spectator, so we've got carbonate. The nitrate's a spectator, so we've got plus calcium going to form. Look, they did it in this order on purpose because they knew people will put carbonate calcium over here. Don't be silly, right? The positive ion goes first, and so this is calcium carbonate as a solid on the product side. That's it. That thing happens to be balanced already. There's one of each sitting there, and so we're in pretty good shape. Then we get to B. B asks us to look at a diagram. Gives us this diagram and says, draw on the species needed to accurately represent the major ionic species remaining in the solution after the reaction has been completed. So they've got sodium and nitrates here. They have our solid sitting on the bottom. And so we've got to look up and go, this guy is in excess. This calcium nitrate has to be in excess because it told us that it's in excess right above it. Good. And so when we look down here in solution, we have 2 sodiums. Right? See how we have 2 sodiums here? So that means we had one of these. If we had one of these on this side, that's going to determine how much product we get. And so for one of those, we got 2 sodiums coming out of it. And we should have got 2 nitrates coming out of it. Okay, so what we should have got is 2 of these nitrates. What did we actually get? We actually got, in the drawing, 4 nitrates that came out of this. And so that's the key to telling us how much excess of this we had. Because the sodium reacting with this was going to provide us with 2 nitrates. We got 4, which means we had excess of this, right? We needed to provide an extra 2 of these. So this was a 1-to-1 ratio that reacted. It meant we had a whole one left over, so we started with 2 worth of those things. And so this one produced 2 sodium nitrates, where those nitrates are from, and we had 1 leftover calcium nitrate. That means there's the extra 2 excess nitrates, so there's our 4 total nitrates, the 2 from here plus the 2 excess, which means we had 1 extra calcium. So the only thing that needs to be added to this drawing is 1 calcium ion floating around. Go back, that takes a second for you. Go back and talk yourself through that to make sense out of it. Good. One of those would have produced 1 calcium carbonate, 1 piece of solid. It would produce 2 sodiums and 2 nitrates in solution. We had 2 extra nitrates. Where did those extra nitrates came from? They came from having 1 more calcium nitrate than we needed. And really we're talking in moles, right? 1 more mole of calcium nitrate than we needed. That's part B. You got a point for coming up with just a calcium ion floating around in that solution somewhere. You should have known it was in excess, right? And so we should know that the carbonate was not floating around anymore. The sodium and nitrates are always floating around, they're spectators. It's a matter of figuring out how many calciums should be sitting in there. You do that based off the nitrates. That's a lot of words. Sorry. Go back through and make sure you're comfy with that. Then we get down here, the student filters and dries the precipitate of calcium carbonate and records the data in the table below. It says determine the moles of sodium carbonate in the original 50 ml solution. So we've got volume of 50 mils, volume of the calcium nitrate that was added, 100 mils, mass of the calcium carbonate precipitate. If we know how much was precipitated, then we can go back and figure out how many moles we had of the sodium carbonate from the balanced equation. And so here we go, our 0.93, this is part C now, our 0.93 grams of calcium carbonate, and we're going to take those things and figure out how many moles must have been in the original sodium carbonate. That's what they want. So we're just using this balanced equation. We have this, we're going back towards sodium carbonate. They're a 1-to-1 ratio of moles, which is nice for us. So we got grams of calcium carbonate to moles calcium carbonate. I tell you guys that this one shows up a lot because it's 100 to 1 mole, even though we won't have any multiple choice to do this year. Makes me sad too. Moles of calcium carbonate will come down and we will go to moles of sodium carbonate, what we wanted. That happens to be a 1-to-1 ratio from the balanced equation. Calcium carbonate to sodium carbonate. And so we can even do that in our heads. That gives us 0.0093 moles of sodium carbonate. Stick a unit on that thing. Make sure you're good. That's all they're asking here. Determine the number of moles of sodium carbonate in the original 50 mils. The student realizes that the precipitate, ready? The precipitate was not completely dry and claims that as a result the calculated sodium carbonate molarity is too low. Do you agree with the student's claim? And the answer is no. I don't agree with the student's claim. And so here on part D, what they're saying is if you weighed that precipitate and it wasn't all the way dry, would that give you more or less moles of the sodium carbonate at the end? If it wasn't all the way dry, that mass is bigger and therefore the moles of the sodium carbonate would be bigger. You have to put that into words, which is no fun. So would it be smaller? No, I disagree. Not drying all the precipitate would give it a bigger mass. And therefore, we'll triangle with dots, and therefore a bigger calculated moles. I'm going to put calculated molarity because that's what the question asks. Calculated molarity of Na2CO3. There's that question again. Student realized the precipitate was not completely dried. The calculated molarity is too low. False. Why? Adding mass, because not drying it means there's water weight in there. Adding the mass means your mass of the precipitate is too big, and then you'd get a bigger molarity of the sodium carbonate. That's it. And then the last little piece, part E, says after the precipitate forms and is filtered, the liquid that passed through the filter is tested to see if it can conduct electricity. What would be observed? Would that solution conduct electricity? Yes. Why? Look at, there's all of these spectator ions floating around, plus some calcium ions floating around. So E is the solution would conduct electricity, electricity because the spectator ions are still present in solution. That's how I'd write that. That's it. Those are all 1 point apiece for the first 5 parts of that problem. So you can tally them up, see how many you got out of those 5. We'll talk to you soon.